Hello, in this video, we are going to continue the discussion that we had in the last video, where we were talking about how to relate RDFS language with logic, right? And we did that with a specific purpose, basically to understand the semantics or model the semantics of RDFS language or the vocabulary items that are there in the RDFS language, right? So, some examples of these vocabulary items are like say RDFS subclass of, RDFS property, RDFS subproperty of, all those things, right? Now, in the last video lecture, we have tried to see different kinds of entailment rules or deduction rules related to simple entailment and RDF entailment. Now, here we are focusing on the entailment rules for RDFS language. And we have already talked about the axiomatic triples that should be inserted or that will be assumed to be true always concerning the RDFS entailment, right? Or basically the triples that are true if we consider RDFS language. So, for example, let us revisit some of the triples that we have talked about in the last video. For example, this RDFS subproperty of it is having range to be RDF property, and we have tried to explain the meaning of all these triples. Not all these triples, I have given you some examples, but you can follow those examples to deduce the meaning of the other triples, right? I hope you can all do that. Now coming back to the other rules of RDFS entailment. So the first rule that we will be starting with is called the rule for literals, right? So we have taken care of the literals or a kind of literals in when we define this RDF entailment rules, right? So there we had a rule for XML literal. So in RDF we have something called RDF XML literal class, right? We have something like this, right? So what does this class consist of? It consists of all the XML data types, right? Now this literal or specifically this RDFS literal is the class of all the literals. So in that sense, this RDFS literal is a superclass of all these superclass of all this RDF XML literal. So you can write something like this. So this is RDFS subclass of, and it is RDF XML literal, right? So this is the kind of relationship that exists between RDF XML literal and RDFS literal. But in a generic sense, you can think this RDFS literal to be more generic than this RDF XML literal, right? Now let us look at this particular rule. What is it saying? Is it saying that if you have a triple like UAL, you have a triple in UAL where L is a literal, then you can say that something is of type literal. This something is of type literal. But this you have to apply keeping in mind the literal generalization rule. So this rule we have studied in RDF entailment. So this literal generalization rule is a rule which we marked as LG. This LG rule is has been defined in RDF entailment. What was that? So if you have something like this UAL, then you can say that UA. So you can weaken this particular. You can weaken this particular L and replace that L using a blank node. And you know that every blank node has an ID, right? So if you have assigned this underscore colon n to be the ID that is used to weaken this L, then you have to use the same ID, this n, here in this rule, right? So you have to reuse the ID that you have used earlier to generalize or weaken the literal L, the same literal, right? And this is what the condition for applying this particular rule here in RDFS, right? Now, as we know that we can impose different restrictions on a property, and what are the kind of restrictions we can put? So one restriction is the domain restriction, and the other restriction is the range restriction, right? So let us look at how we model or how we interpret the domain restriction. So this is the input triple UAY, right? And this is what also you are saying to be true. And what is that? That A has got RDFS domain, or in simple term, the domain of A, and A is a property, right? So the domain of A is X, and what is X? You know that X is a class, right? So this is a class. So if these two are true, right? So you can implicitly assume that there is one AND, logical AND between these two triple, and these two triple, if these two triples are true, then this is what you can deduce. What you can deduce, that U, this particular U is of RDF type X. So this U is an instance of the class X. So this is what we say, right? So what we can infer here, that U, this is a resource, U is a resource, U is an instance of class X, right? Now can we draw this? Let us draw this. So this U is a resource, right? And this A is a property, and Y is the object, right? Now what we are saying? We are saying that this A has got domain. This A has got domain. I am skipping this RDFS part, so I assume that that is there. So this has got the domain to be X. And what is the type of X? So the RDF type of X is basically RDFS class. So I'm skipping all these prefixes, assuming that you understand this class to be RDFS class, right? Now, what we can infer, so this is true. Let me put this as solid line. Now, what we can infer? We can infer that this U is a type of X, and in language term, we can say that U is an instance of the class X, right? Now, as we can have domain restriction, we can have also range restriction, and it will be kind of similar, right? So this is the triple you have that is assumed to be true, U, A, Y, and you are saying that A has got the range to be X, and in that case, this Y should be an instance of the class X, right? So this Y is an instance of X, right? Now, we know that everything what you can see in semantic web is a resource. So how to model this? So you have an input triple UAX, and if you have something like that, you can assume or you can deduce that U is an instance of RDFS resource, because RDFS resource is the class of everything. So everything comes under RDFS resource. Similarly, you can say that this X is an instance of the resources class, right? And of course, this A, which is a property is also an instance of this resource, because of the very fact that everything you can define on the semantic web belongs to the resource class, right? Now we know that we can define property hierarchy. So we can define one property to be sub property of another property, right? So let us see what are the kind of rules that are relevant to this property hierarchy. So basically, this is relevant to property hierarchy. Property hierarchy, right? So we say that sub-property relation, so this is also a relation. This holds between two properties. So P1 is a sub-property of P2, right? Now this relation is transitive. So what we say that P1 is a sub-property of P2 and P2 is a sub-property of P3, and from this we can infer that P1 is a sub-property of P3, right? And it is very easy to model. So if U is a sub-property of V and V is a sub-property of X, from that I can infer that U is a sub-property of X, right? Now sub-property relation is reflexive. So when we say that some property is reflexive, some relation is reflexive, if you have, and we know that we can represent a relation as a set of tuples, right? Here you can have say P1, P2, you can have say P1, Px, so on and so forth. But also you can assume this to be true, that P1, P1. So when a relation contains, sorry, it will be, yeah, P1, P1. When a relation contains a tuple like this, where all the entries in this tuple are the same, then that relation is called reflexive, right? Then that relation is called reflexive. So the sub-property relation is a reflexive relation. And how do you model that? So we say that U is an instance of RDF. So it will not be RDFS. You can strike this out. RDF property, then that will deduce this fact that U is a sub-property of U, right? So this is basically concerning this tuple in the relationship, right? And this relation is what? This relation is basically the sub-property relation, right? Uh, so when we have a property which is a sub-property of another property, then there is another interesting relation that exists between these two properties. So what I'm saying, that this A is a sub-property of B. So A is a sub-property of B, right? And this is what you have. You have U is connected to Y via this property. So this is the triple visual form of this triple, right? If this is so, what you can infer? You can infer this also, right? So you can say that U and Y, they are connected via B. So what would be a very simple example? So the simple example would be like this, say mother of is a sub-property of say parent. Now if you say that X is mother of Y, from this you can infer that X is also a parent of Y, right? So this is what we call as inheritance in the property hierarchy. Now similar kind of relationship you can define for the subclasses, right? There would be some other relationships that are, or rules that also hold true for the subclass. So let us see what are the kind of rules that are that are true for the subclasses in RDFS, right? Now this is what we can say, that every class is a subclass of the RDFS resource. This is we know to be true, right? So if we see that any resource U is an instance of RDFS class, then this U is a subclass of resource, right? So we say that albums, right? So you have album, so EX album. So what is this? This is basically a subclass of, or it is an instance of RDFS class. RDFS class. And from this, what we can do, we can infer that this U is a subclass of the resources class, the resource class, RDF resource class, right? Now, as we had inheritance in property hierarchy, we have inheritance in class hierarchy also. So how do we model that? So let's say you have a relationship between two classes, which is U and X. You are saying that U is a subclass of say X, right? And you have some resource, say V. V is an instance of U. So this is of type U. So V is an instance of U, or V is of type U. So from this, what you can infer? You can infer that V is also a type of X, right? Because of the very fact that U is a subclass of X, right? So you can think about a very simple example, like you have person to be the to be one class and man to be one class, right? So this is the class of man and this is the class of person, right? Now, as you have something like this, that you have say V, say U to be member of M, then you can deduce that U is a member of P also, right? Now, as properties, they are the sub-property relation is reflexive. Similarly, you have subclass relationship to be reflexive. So, a class is a subclass of itself. So, this is how we are saying if something is of type class, then that is a subclass of itself, right? And as we know that the sub-properties are transitive, the sub-property relationship is transitive, subclass relationship also transitive, very simple to follow. So if you have C1 to be subclass of C2 and C2 to be subclass of C3, then you can deduce that this C1 is a subclass of C3, right? There is something special in RDFS, which is container. We have talked about this earlier. So this basically contains open container and the list, right? Open container and list, right? So all these are modeled using something RDFS container membership property, right? Now, there is another thing which is called RDFS member, and let us see what is the relationship between this RDFS container membership property and RDFS member. Now, can you tell me what this RDFS container membership property is? It is a class. It is a class of a set of properties. But this RDFS member is a property. See, this RDF member is a property, right? Now, if you have something like this, say one resource U is an instance of container membership property, and as this is a class, this is a very valid statement, that is one particular resource is an instance of this class. And what kind of thing will this be? This will be a property, right? Because of the very fact that this particular thing is a class of properties. So this is a property, right? And as this is a property, it can be a sub property of another property, right? And what kind of statement we can make about this particular thing, this particular property? We can make a statement like U is a sub property of RDFS member, because of the very fact whatever the properties that are coming inside this container membership property, they are used to model membership of some resource into a class, right? So let us try to illustrate this further visually. So you have container membership property, and of course it is a type of it is a subclass of property, right? It is a class. So first of all, it is a class, right? And what kind of things that are there inside? You have some properties inside this, right? That's why it is a subclass of the RDF property, right? And what kind of property that are included in this class? Basically the properties that we use to model this RDF bag, RDF say sequence, RDF sequence, or RDF alt, right? So these are the things we when we model these constructs, we make use of these properties, right? So basically you say that something, the RDF1, RDF uh, want to be say Virat. So this was the example we worked with, right? Then say RDF2 to be say Shami, right? So you see these are the properties, and what they are trying to mean, they are trying to mean that these are part of some container, like say it can be a part of bag, or it can be a part of sec, or it can be a part of alt, right? So that's why they are coming under this container membership property, right? So these are all instances of container membership property, right? And all these, this RDF1, RDF2, RDFN, they are sub property of RDFS member, right? And this RDF member is a type of container membership property, right? So this is the kind of relationship holds between this container membership property, the property class as a whole, the individual numbered relation for this bag sequence and all. So these are the kind of relations, and the RDFS member, right? Uh, there are some other rules related to the literals. So one such rule is, say U is of RDF type data type. So for example, say integer. This U can be say class of integers, right? So this U is, this integer is a type of data type. If that is so, then you can say that U is a subclass of literal. So you can say that this integer class is a subclass of the literal class, because they are used to represent what? They are used to represent the values, right? Likewise, you can think of say string, you can think of other things like late date, other things, right? So these, but the next rule, which is reliterization reliterizing blank note. So it is a kind of reverse rule for LG. So in LG, what we did, we weakened a literal to a blank note, right? Here we are doing the reverse. Uh, uh, we are strengthening the blank note by assigning a literal value, right? So this particular rule, this has been added to this RDFS entailment rule set in a pretty later stage, and it is not very clear at this point of time why this rule is important and what are the kind of uses of this rule. But for the sake of completeness, let me talk about this. So this rule is basically, if you have something like UAN, you can reliterize this by replacing this underscore n to L, provided that this particular ID was used to weaken the same literal, which is here in this case L. So this is the constraint, right? But again, it is not very clear how this rule is relevant and how this rule can be applied, right? So these are the kind of set of rules. There are kind of 13 rules in RDFS entailment. Not 13 rules. There are numbered 13 rules, and along with that, you have got this GL, right? Now, similar to what we had for the theorems, the entailment theorems in RDF and simple entailment, we have an entailment theorem in RDFS also, and it is kind of similar kind of statement that you can make, that a graph G1, that RDFS entails a graph G2 if G1 can be extended to G1 prime by applying rules like LG, GL, RDF, AX, which is the axiomatic rule from RDF1 to RDFS 13. So we are clubbing all the RDF and RDFS rules together. So this LG comes from RDF. This RDF1 and RDF2, they come from RDF. But the other rules like GL, RDF, AX, and RDFS 1 to RDFS 13, they belong to, and of course RDF SAX, they belong to. So these also belong to these three set, they belong to RDF, and rest of the rules like RDFS 1 to RDFS 13 and RDFSX along with this GL. So this GL, this RDFSAX, and this RDFS1 to RDFS13, they belong to RDFS, right? And you apply these rules to convert G1 to G1 prime, and after that, if you see that G1 prime simply entails G2, then you can say that G1 RDFS entails G2, right? So in that sense, you can say that if some graph, say G1, is RDFS entails G2, then you can say that G1 RDF entails G2. So RDF entails G2, and also you can say that G1 simply entails G2, right? So this is what you can say. So let us try to visualize as we have done earlier. So this is your G1, G2. You convert this G1 to G1 prime by applying all the rules we have mentioned. And from this, if you say that G1 prime simply entails G2, then you can say that G1 entails G2. Now to illustrate all these, I will not say all these. So you have a set of rules and you have a knowledge graph. So this is your knowledge graph, which is existing in your knowledge base. And what we will be trying to do, we'll be having a query and try to see whether that query can be answered based on this knowledge graph, right? So let us try to illustrate what this graph actually do, or what this graph actually models, right? So what we are saying, that Oppo is a sponsor, Oppo sponsors Indian cricket team. So these are concrete entities. And Indian cricket team has all-rounder member who is Hardik, right? And this Oppo is an instance of smartphone company. So this is a class, right? And this all-rounder member, it is a property which is a sub-property of has member. And this has member is a type of container membership property, right? So this is what we know. And this all-rounder member has got domain to be cricket team and range to be all-rounder, right? A cricket team has all-rounder or an all-rounder, right? So this is the knowledge graph you have, right? So this knowledge graph can be flattened out by enumerating all the triples that are there, right? So this is what we have done. So this is your G1, right? Now, what is your G2? G2 is basically the query graph, right? And what you have in the query graph? In the query graph, you are trying to ask, is there a smartphone company that sponsors a cricket team having an all-rounder in the team, right? So we know this is a concrete thing that we can get, that is smartphone company, so which is basically the class smartphone company, and you have got an all-rounder in the team, something that is of type all-rounder. But the other thing like this, uh, these are a kind of blanks which we need to fill up, and if we can fill up, then we basically can answer the query, right? So what we will do, we will be iteratively applying different rules to deduce new facts, and we'll be using these facts to deduce other facts, and finally we'll be, so we have G1, and from this G1 we'll be applying all the rules to get G1 prime. So this is the kind of objective that we have in the first hand, and then we try to see whether G2 is a subset of this G1 prime, right? So let us see, this is the kind of concrete triple we have. Indian cricket team has all-rounder Hardik, and this all-rounder member has got range to be all-rounder. Now we can apply this RDFS 3, which says that if this is a triple which is true, U, A, Y, and A has got the range to be X, then this Y would be belonging to the class X, right? So what is Y in our case? Y in our case is Hardik, right? And what is X in our case? X in our case is all-rounder. So from this we can deduce that Hardik is an instance of the class all-rounder. So this is the thing we have deduced, right? Now the next uh, triple we can have our attention to is, has team member is of type container membership property. Now look at this rule. So if U is of type container membership property, then U is a sub property of RDFS member, right? So from this we can deduce that has team member is a sub property of RDFS member, right? So whenever we have uh, has team member, we can replace that with RDFS member, right? Now again we have got something like this. All-rounder member is a sub-property of has team member, which has been declared right earlier, and has team member is a sub-property of member, which we have deduced just right now, right? Now if you combine these two using the transitivity, so here using the transitivity of the sub-property relation, right? We are using the transitivity of the sub-property relation, and from that what we can infer, that has all-rounder member is a sub-property of RDFS member. So we can replace this has all-rounder member by RDFS member, right? Now this is what we have just deduced, has all-rounder member sub-property of RDFS member, and we have something like Indian cricket team has all-rounder Hardik, and from these two we are using what? We are using the inheritance, inheritance in sub-property. We are using inheritance in sub-property, right? And if we use this inheritance, we can deduce that Indian cricket team has got a member who is Hardik, right? So this we have deduced. Now let us apply the rules that are that we can pick up from the simple entailment, right? So Oppo sponsors Indian cricket team, and from that we can deduce that someone sponsors Indian cricket team, right? Also we can we can deduce from Oppo is a type of smartphone company, that Oppo, or underscore n is an instance of smartphone company. Now you can look at something interesting which is called novelty condition, which is a kind of condition we have imposed while we were weakening a concrete entity with a blank node, right? So there we used the novelty condition. So here we are reusing the node ID because we are weakening the same entity here, right? So that's why we are using the same node ID, right? So from this we can say that someone has is an instance of smartphone company, right? Now we have this we can use this now. Someone sponsors Indian cricket team, and we can weaken this Indian cricket team by replacing it with another ID underscore colon n1, and we are saying that someone sponsors something, someone, right? Now, from the fact Indian cricket team has all-rounder member Hardik, we have used N1 to weaken Indian cricket team, and we'll keep on using this ID whenever we are weakening Indian cricket team in other triples. So we are weakening Indian cricket team by underscore N1. We are saying that something has all-rounder member Hardik, right? And from this something has all-rounder member Hardik, and has all-rounder member is having range to be all-rounder. From this what we can deduce? We can deduce that Hardik is a type of all-rounder. Hardik belongs to all-rounder, right? And then you have this we have already deduced, like something has got member to be Hardik, and from this we can again weaken this Hardik to assign a blank node ID into, because this is another instance we are weakening, right? So this is what we can infer. And from the very fact that Hardik is of type all-rounder, I can say that someone is of type all-rounder, or something is of type all-rounder, right? We are using this same node ID N2 here to weaken the same entity or same URI, right? So with repeated application of this rule, so these are the set of base triples. So these are the set of base triples that we had in G1, and we are adding this triple by the process of entailment. So we are adding this by the process of entailment, basically by applying the rule that we know to be true for RDFS, RDF, and simple entailment, right? So this is your graph G1 prime. Now this is your graph G2, and you can easily see that this G2 is a subclass of G1 prime, and you can say that your query is answered, right? So let us stop here. So we have talked about the entailment rules, basically the simple entailment. Then you have the RDF entailment and RDFS entailment, and you have provided examples through which we can illustrate how we can use these rules to transform a graph into another graph. And if we see that the query graph is a subgraph of the transform graph, then we say that the query has got an answer, right? So in the next video, of course, on this same topic, which is basically the relationship between RDFS language or the vocabulary with the logic system. So we will talk about how we can use first order logic to model the constructs or the truth about the RDFS vocabulary. Thank you very much.